Moving into chapter 20. We're going to break up the organization on the subsequent chapters a little bit differently. Instead of dealing with nomenclature, we'll put that at the end of the lectures. If for some reason you want me to talk about nomenclature, which is probably a bad idea on your part, then I can go ahead and do that at the end. But ultimately, nomenclature is rules. The textbook knows the rules a heck of a lot better than I can. It's going to make more sense to use the textbook to figure out how to name things than it is to talk to me. Okay? So what we'll go through and do is look at kind of a general overview on what's happening. Then we'll look at some of the chemistry. Hopefully what we'll cover today is enough to get you through a good section of the homework and then be able to take good educated guesses on the rest of the homework. Okay? That would be the hope as far as how far we'll get. Okay? The plan will be to have a longer multiple choice quiz on Wednesday of next week covering all of chapter 20 in theory. Okay? So to get you guys that practice, we'll then break it down into a group quiz, divide up some problems, write up answers on the board, that kind of fun stuff. Okay? So aldehydes and ketones, really, really important functional group, arguably the most important functional group, or the carbonyl is the most important functional group for any kind of medicinal purposes. Why? Carbonyl is what links, or that chemistry is what allows us to have proteins, amino acids, that's proteins, DNA, sugars. Almost all of the functionality that we think of when we think of life or biochemistry comes from the chemistry of the carbonyl functional group. Okay, so it is incredibly important to understand what's going on with these. So your textbook goes through and lists a whole bunch of different things that have carbonyls. This compound, kind of fun. Well, vanilla, you've already seen that one with our vanillin. The cinnamon flavor, we're looking at trans-cinnamaldehyde. If you go through and want to practice spectroscopy because your spectroscopy score was really bad, you might go and look at that spectroscopy packet that I posted way back when that reviewed and gave you 10 to 15 problems. Interesting point of truth. The spectroscopy problem that was in your exam pulled directly from that packet. Okay, verbatim, copy and pasted. Okay, so if you do that practice, that should help you because I'm lazy and probably won't build more difficult problems. So we get a lot of different flavors coming from these. Ultimately, these are all biological sources. Again, carbonyls. Found in pretty much everything that has to do with life. Okay, so important in that respect. Let me put up the names. How did you get these names from those structures? Just as a nomenclature reference. Is it IUPAC? No, it's a common name. Okay, you're not expected to know those names or be able to name them or either direction, either going from the name to the structure or the structure to the name. Just be kind of aware that your textbook may make reference to certain compounds, just like you can with everything else. Look it up. Okay. Preparing aldehydes and ketones. We have made these a couple times before. Okay? In fact, several times. You guys remember any reagents? Just stop you from reading. You remember any reagents that can get you a carbonyl functional group? PCC and chromic acid can both get you carbonyls. What's the issue with chromic acid? It's a stronger oxidizing agent. You won't get the aldehyde. Okay, so that'll push you all the way to the carboxylic acid. Okay? With the PCC, it's a milder reagent, so you can get the aldehyde carbonyl as well as ketones. Other reagents that get you carbonyls. Cold permanganate, okay, will cleave an alkene structure. Okay, split it to the point, since I've got an alkene on here, kind of, it's probably in a very bad place because its chemistry changes. But if we had just the alkene, your permanganate can cleave through the middle there, and we can separate our double bond, and we can put 2 oxygens in our middle. So our permanganate does that. There's another reagent that does that. What's that other reagent? Ozone will do the same thing. Ozone, we can change its chemistry a little bit more. It's not just ozone. We have to follow it up with a secondary reagent. Ozone will generate, once it reacts with the alkene, an odd-looking intermediate, very poorly drawn, but close enough. Okay, you get that 5-membered ring. Okay, that's all ozone does. So when you think carbonyls, what are you thinking about when you react with ozone? It's the subsequent reagent. Do you add an oxidizing agent or do you add a reducing agent? Okay, depending on which one you add, you'll end up with either the acid or just your standard carbonyls, your ketones, okay, and aldehydes. Other reagents. How else can you get a carbonyl? Good call. We could acylate. Acylate's kind of cheating. Why is it cheating? You started with the carbonyl. Okay. So when we do an acylation reaction, we're putting a carbonyl onto an aromatic ring, but our reagent started with the carbonyl to begin with. Okay. So we have a variety of ways to already get these carbonyls. One of the bigger ones that you guys missed, two big ones, would be your mercuration and your boration reaction. So your mercuration and your boration, those can get you carbonyls. Okay, but wait, you might be thinking, mercuration and the boration put on oxygens. They replaced a pi bond and put on an OH. That was true when the pi bond was a double bond. What happens when we make it a triple bond? In the case of the triple bond, we don't get the alcohol, we get the carbonyl. Okay? So just kind of be aware of those. It's an extra way that you can get that carbonyl functional group while starting from an alkyne. So kind of neat. Okay? The next part of this is really kind of addressing how they can react. Okay? So when we look at an individual carbonyl, they've got one drawn out nice and neat for us. And they've even drawn on the answer, which I don't like, but oh well. Okay, we've got our carbonyl functional group. So when you look at that functional group, what should you be identifying right off the bat? Make it big. Okay. I like the pi bond as a source of reactivity. Would we expect it to react like an alkene? No, why not?
You get that electronegativity difference.
There's a big difference in electronegativity. So we do have the reactivity of that pi bond, but that reactivity is largely going to be making our oxygen pick up electron density. And we end up with our negatively charged oxygen, which means we now have what? That oxygen can act as, we now have the potential for it to be a nucleophile. What else can it act as? Our Bronsted base. Okay? So we've got chemistry in that oxygen in that case. Is it acting as a nucleophile going to be particularly likely? Does oxygen want to give up its electron? No. So while we do have that negative charge, that oxygen has the potential to act as a nucleophile, but it's rather limited. Okay? And that's because we have that uber reactive carbon from our positive, okay, trying to hold a lot of that electron density, which limits the nucleophilicity of that oxygen. Okay? So we have the potential for a Bronsted base. For the oxygen to become negative, what else has to happen?
Carbon has to be positive.
Carbon has to be positive. What happens to the carbon if it's positive? What do we have now?
Electrophile.
We have an electrophile, also known as?
Acid.
I want a little bit more than acid. What'd you say? It won't be Bronsted. For it to be Bronsted-Lowry, we have to have a hydrogen attached to that carbon. We don't have that. So it's a Lewis acid. Okay? So our Lewis and our electrophile are effectively the same thing. Let's call them equals. And we're just going to call it Lou for the moment. Okay? I don't care what the hybrid looks like, so you don't have to worry about that question. So what we're concerned about is looking at that negative and positive and trying to predict now these potential reactions. Our oxygen can act as that base, and our carbon can act as an electrophile. Okay? So what are the two reagents that we might add to react with a carbonyl? Okay, we could do the sodium borohydride. Okay, that's an interesting idea. I don't quite want to get to that yet. It's too specific of a reagent. I want a general class. What things would react with Bronsted bases? Bronsted acids. Okay, so we could throw in something that's acidic. That would react with the carbonyl. What would the result of that be? Okay, water and salt only works if it's H plus and OH minus. We'd end up with the OH, right? What happened to our carbon? That carbon would have to be positively charged still. Okay, all we did was reacted with the basic end of our oxygen. Did we do anything with the carbon at that point? No. So what does adding an acid do to the reactivity of that carbon? Makes it more reactive. Why? There's now less potential for resonance to stabilize that positive. That oxygen's electrons are now being shared with the hydrogen instead of with the carbon. So when we have our oxygen act as a Bronsted-Lowry base, we end up making our carbon of our carbonyl more electrophilic. We can speed a reaction by adding an acid, which means the acid would typically act as catalyst. Okay? So we're going to see acids and bases affecting our overall mechanisms as far as catalysts go. Okay? So what is that going to really drive home? When we think about the carbonyl chemistry, what's the most important aspect? That it's a Bronsted-Lowry base or that it's an electrophile?
Base.
If it acts as a base, what does it do to the electrophile? Makes it more electrophilic. The carbon doesn't, or the oxygen doesn't really want to give up those electrons anyway. So when you see a carbonyl, what you should be thinking is electrophile. That is the primary thought process that should be going through. You have that carbon that is electrophilic. You need to stabilize that partial positive. What do you need to, or depending on the structure, formal positive. What do you need to add to stabilize that positive? How do you stabilize any positive? You need to supply electrons. So we'll see these species reacting with nucleophiles. Okay, so that's our big kind of conclusion behind carbonyls. Everything that we're going to go through in this chapter is a new nucleophile, new nucleophile, new nucleophile. What nucleophiles have we seen before? Borohydride supplied. Hydride, H minus. Is H minus a nucleophile? Yep, there's a nucleophile. What other nucleophiles have we seen? OH. The oxygen can act as a nucleophile with that negative charge. So we can see hydrogen as nucleophiles. We can see oxygen as nucleophiles. Nitrogen can be seen as a nucleophile. Again, lone pairs. There another one? Actually, a couple more. What other atoms carry negative charges typically? They're halides. Your halogens can act as nucleophiles. We've got to be a little bit careful with the halogens, though. What's special about the halogens? They're good nucleophiles, but they're also good leaving groups. So while we could have it come in and attack, they could be chased away just as easily. And we'll look at that in a second.
So if you add hydrochloric acid to this, the chlorine wouldn't really attach?
Yeah, you don't see a large percentage of that. Yep, and we'll talk about that. Okay, last nucleophile. Big nucleophile. You did a lab on it. Don't typically see a negative charge. Sulfur is going to have the same reactivity as oxygen. It's a good nucleophile. It's actually a better nucleophile than oxygen. Grignard reagent. What's our nucleophile with the Grignard reagent? Carbon. Okay. So we're going to look at hydrogen, carbon, oxygen, and nitrogen all as nucleophiles. We'll briefly look at the halogens as nucleophiles, but we'll step away from those, and hopefully we'll see that in a little bit. Okay, some things to kind of watch out for. First off, this is describing, again, that polarization. The next thing that they're kind of getting at here, which your textbook might discuss, and you might see it show up in other texts as well, is that our nucleophile can come in and attack that carbon. Okay, what's the geometry around that carbon? Trigonal planar. So it's interacting with the lobe of the p orbital that is currently above that plane. Is there a lobe below it? Yeah, so that nucleophile could have just as easily come in from the bottom. Is that going to have an effect in the overall product? Yeah, stereochemistry could potentially show up. Okay? This attack of top versus bottom with carbonyls is not something I'm going to directly test you on, but you will see a reference back to this on which face of the carbonyl it's reacting with. I really wish I had spent the time to look up what those faces are called, but they get two particular names, and it all comes down to what's the end result. Okay, what stereocenter do you end up with at the end? If you end up with the R stereocenter, then it attacks from the X face. If you end up with the S stereocenter, then it attacks from the Y face. Okay? So X and Y sometimes get those special names. Okay? The important thing to realize is there a difference between our X and Y positions? Nope, it's trigonal planar, which means more than likely what's going to happen if we've got stereochemistry in our product? Half of each. We're going to end up with a 50-50 mixture, also known as racemic. What's the optical activity? No optical activity. Okay? So kind of be aware of those repercussions of these. If we now take a look at these two carbonyls and we want them to react as electrophiles, would we expect one to react faster than the other?
The one on the left.
The one on the left should react faster. I agree. Why? Steric hindrance. Okay? Resonance explains why that carbonyl is reactive, because we can push electron density on that pi bond up to the oxygen. But we can do that with both of those. So in this case, we can't use resonance to explain why the left one reacts faster. Well, if resonance doesn't work, what's your next best option? Steric hindrance. Where's the steric issue?
You got those two large groups on the one on the right, whereas the left has only got the hydrogen on the left.
We're comparing our hydrogen versus that tert-butyl group. The tert-butyl is much larger than the hydrogen, which means it has more electrons. As our nucleophile comes in, it can butt up against that and get repelled and never get in to react with our carbonyl. Okay, so that's going to affect the reactivity. Along those lines, okay, we see a very dramatic difference as far as reactivity between these two. Typically, if we have large differences in reactivity, we come up with different names for these. What type of carbonyl do we have in each of these cases? The aldehyde is which one? Our left. And our right is the ketone. Have we seen other carbonyls? What if I'd done something like that? How would we expect it to react? Functional group? What's the name of this functional group?
Carboxylic acid.
It's the ester. For it to be a carboxylic acid, that now orange R group needs to be a hydrogen. Okay? Since we're looking at carbons out there, we're looking at that as an ester functional group. Which one would we expect to react faster? The ester, the ketone, or the aldehyde, now that we've added the ester in there? Okay, why do you think the ester would react faster? Okay. Probably. We're seeing 2 electron poles, right? So that might make sense. Okay. There's a reason I said might. What's the might? We still have steric hindrance. What's your statement?
Having the other oxygen also contributes some of its electron density back towards the carbon going up.
If we pull the electron density from that pi bond and put it up on our oxygen, we do get that positive carbon, just like we get with the others. What's the one extra thing that our ester gives us that the other ones don't? We have that lone pair, in fact 2 lone pairs in that oxygen. One of those can donate in and stabilize the positive charge. If it becomes stable, what does that do to the reactivity? Decreases it. Go back to your Grignard reaction. Okay, I think it was the extra credit question. I asked why when you reacted the ester that you got the result that you got. Okay? The reason is that in the process of running your Grignard reaction with an ester, you form a ketone. Which is more reactive, the ketone or the ester? The ketone. So as soon as the Grignard reacts with the ester, it makes a ketone, and now the ketone product reacts with the Grignard preferentially over the ester. So we don't end up reacting all of the ester. Okay? So I would recommend that you look at that from the lab and kind of get an idea on what's happening. Okay? Would not be surprised if that showed up again, say maybe on exam 3. Hi, questions about that? Hi. So here's our halogen acting as a nucleophile, our iodide coming in and attacking. So this is one of the reasons why I think this chapter, and the next chapter for that matter, are a little bit more difficult. Our iodide can act as a nucleophile, good source of electrons, very polarizable. We're even reacting with an aldehyde, so the more reactive of our carbonyls. In the course of that reaction, the iodide donates its electrons, forms that bond. We have to break the pi bond, and we get the negative oxygen. Okay? Now that we've done that step of the reaction, this is where 152 comes into play. We now have to decide, is the product that we made a good product or a bad product? Okay? And that decision is a little bit tricky. Okay? Some of that good product, bad product is, does it look good? Okay? It's usually passable for everything up to this point. Okay? I would say, argue even in this case, we could probably pull a does it look good? Which product or which species looks better? Are iodide attacked or not attacked? Okay, a reactant looks a little bit better. Okay, so now we have to come up with a better or a reasonable explanation for that. Why would we see the reverse reaction? Why, if we look at this at equilibrium, here's your 152 material, why when we look at this reaction we see no result? We get very, very little product. I is a great nucleophile. It's also a good leaving group. So the hydrogen's definitely not going to leave because that would be H minus. Okay. What else would we be looking at? What makes our reactants reactive? The charge on what atom?
Positive on the carbon.
No, there's not a formal charge there.
So the partial positive on the carbon.
There's something that's more reactive than the partial positive. The iodine. The iodine is negatively charged. That's going to be what drives that reaction, is that nucleophile. What makes our product reactive?
Negatively charged oxygen.
The negatively charged oxygen. So what can we go through and do? Let's evaluate. Which one prefers to have the electrons, oxygen or iodine? Which one can stabilize those electrons better? So if we look at our atom effects, electronegativity, sure, we could say oxygen's more electronegative. But before you look at electronegativity, you need to address size. Size typically will trump electronegativity. Which one can hold the negative charge better? Iodine, because it's much, much bigger. What does that mean? Well, the reaction gets to decide. Where do you want the negative charge? Well, we just said iodine would rather have a negative charge. What happens? No reaction occurs. If the iodine does for some reason come in and attack, oxygen just says this sucks being negative, pushes its electron density back down, and it has to kick out the iodine. So we see the reverse reaction. This is one of the reasons why, when we look at our carbonyls, they don't react very well with halogens, because all of our halogens, most of our halogens, are really good leaving groups. Okay? They can stabilize that negative charge relatively well. Okay? They start off with relatively high electronegativity, but then they're also bigger than pretty much everything else. Yes?
Is this a case in which you're going to add something else into it so that if it attacks, you can get that?
So if we absolutely want that iodine to attach, what we have to do is increase the reactivity somehow. So our first issue was what? We said the iodine would hold the negative charge better than the oxygen. So how can we help push the formation of our product? Well, our comparison is I minus versus O minus. What if it's not O minus? Yeah, let's add something that can change that oxygen so that when the iodine attacks and the oxygen accepts electrons, it's not becoming negative. It's becoming neutral. What could we add to the reaction to help facilitate that? An acid. If we put in HI, now the oxygen can react with the hydrogen first as a Bronsted-Lowry base, then the iodine can act as a nucleophile to generate our new product, where instead of having O minus, we have OH. Okay? Does that make it better? Yes. Does it make it better enough? No. Okay. Did you say, can we go back to the first slides?
No, it makes it seem like it kind of goes back to when I was asking about adding HCl.
Yeah. So it does go back to that same idea. We can have the oxygen act as a Bronsted-Lowry base, which makes our electrophile more electrophilic in the hopes that our nucleophile doesn't have to be as strong of a nucleophile, okay, to kind of help push that reaction. Okay, it helps. We do see more of our product formed in that case, but we still don't see a lot. Because again, our iodide is really good at holding that negative charge. Okay. Sorry, other questions on that? Okay. We can show in all sorts of other nucleophiles. Okay, so in this case, they gave you the cyano, or the cyanide, Cn minus. Also a really good nucleophile. What's that structure look like? Where's the negative charge? On our carbon becomes negatively charged. How good of a nucleophile do you think that is? Does carbon want to be negative? No. How good of a nucleophile is that? That's a pretty good nucleophile. It doesn't want that negative charge. It's likely going to push the formation of our product, and we'll lose the carbonyl. Okay, how about H minus? Okay, if we take a look at H minus, does hydrogen really want to hold a negative charge? Nope. Also, really good nucleophile. R minus, what is R minus? What are we saying in that case? It's a negative carbon, and we'll just put off some random stuff coming off of it. Would we expect it to be a better nucleophile or a worse nucleophile than the cyanide? Kind of depends on what the groups are hanging off of that carbon. We said they're relatively small. What's the difference between those carbons?
You have the nitrogen compared to the carbon.
True, but the nitrogen isn't a difference between the carbons. The nitrogen is the difference between whatever's attached to it. What's the difference between the carbons in those two structures? Hybridization. Okay. With our cyanide, our hybridization is sp versus the other one, our R group, sp3. What changes with our hybridization? Effectively, our electronegativity. Our cyanide with that sp hybridization is more electronegative than our sp3 R group. If it's more electronegative, what is that going to do to the nucleophilicity? It's going to decrease. It's now less willing to give up those electrons because it's more electronegative. Okay. The first and the last one, OH minus and H2O, which one's the better nucleophile? OH minus because
Formal charge.
formally negative. Okay? So what we're trying to do is evaluate what's happening in each of those cases. With all of these, what this is the next sequence of questions are trying to go through and do is go through and have those nucleophiles attack. See what the result is. Okay? So let's go through and pick oops. Let's go ahead and do we did our carbonyl. Let's react it with H-. What would our result be? What do you think? Which way should the equilibrium lie, left or right? Products or reactants? Should go to the right towards our products because the oxygen can hold a negative charge better than the hydrogen. So we would probably expect this reaction to push towards the right. What happens if we use OH-? Well, let's not do it in red. What's our product look like now? That was a question. That's why I paused and stopped drawing. What's our product look like? Is there a carbonyl? So what we're going to do is assume it reacts first. If OH- is our nucleophile, what's our product look like? We should have the OH. To get another alcohol, we have to add a hydrogen to it. We haven't specified adding that yet. Okay, what do you think? Where should the equilibrium lie?
To the right.
Okay, right, why do you say to the right?
The other oxygen can spread that negative effect.
Where can you spread that negative? This was an interesting one. Oxygen is negative in both cases. Which way does our equilibrium lie? It doesn't. It's equilibrium. Okay. I believe that it has a slight favoring for our reactants. Okay, but not by much. Okay. What happens if we reacted with water? That's assuming multiple reactions. Okay? So when we go through and do these, you have to do one mechanistic step at a time. You cannot do multiple ones to predict your equilibriums. You will not get an OH at the top because that assumes that you did an acid-base reaction as well. We're only doing the nucleophilic attack. So we get OH, H, with a positive charge and O-. Okay? So all we've done is the nucleophilic attack. If we want to now go through and say, oh, well, what can this structure continue to go through and do? Then we can go back to your thought process and say, oh, that oxygen's acidic. We have to address this first step first. Which way does the equilibrium lie with that first step? What makes our starting material unstable? What negative charge in our starting material?
Partial negative charge.
There's partial negative charge on our oxygens, partial positive on our carbon, but there is no formal charge. Look at your products. What makes our products unstable? Two formal charges. Which way does the equilibrium lie? It's going to go straight back to your starting material. Okay? So do a single step, then evaluate what happens in these cases. And this is something I'm noticing everybody doing. You're propagating it out 6 steps. Okay? In this case, Josh, you just did it 2 steps. And that's fair to be thinking along those lines, but what you'll see with this material is you have to evaluate equilibrium at every single step of your reaction. It goes both forwards and backwards. If it prefers backwards, your forward step does not occur, which means anything you do subsequently is completely irrelevant. Okay? So it's a lot more difficult to process these. You've got to be a little bit more careful and cautious as you draw out your mechanisms, each individual step in particular.
Did we say it favors left too? Because water is a good leaving group?
We could look at it as water is a good leaving group as well. Yep. I personally don't go with leaving groups and typically rely on charges because I think the charges are easier for me personally to see. But you're right, you do get that leaving group effect as well. It's the same effect that we saw with our iodine. Okay. Yours actually probably is more scientific. So kudos for you. Okay. That didn't pop up. So what we can now go through and do is still push some of these ideas of the nucleophilic attack. So they're now showing the OH minus now going through and attacking. Okay. What we said with this one, okay, do we have a good leaving group? Not really. What's the deal with our charges? Charges are the same atoms in both cases. We don't really get a strong favoring one way or the other. So we will probably reach an equilibrium between these, and we don't get anything really productive coming out of it, at least initially. Okay? What happens if instead of it being an aldehyde, we switch it up to, because I don't know when I stopped recording. If we looked at an alkyl chloride reacting, yeah, I knew you were going to do that. Okay, with a nucleophile coming in, doing our backside attack on a chlorine, what's happening? We have that good leaving group in the chloride. What's our leaving group comparison in our carbonyl? It's a little bit odd. Our leaving group is the equivalent of the pi bond on our oxygen. That pi bond leaves and goes on to our oxygen. Okay? So oxygen needs to be a negative charge. So it's kind of a weird comparison, but it kind of works. Oxygen is a negative versus chlorine is a negative. Which is the better leaving group? Chlorine. So when we looked at our alkyl halides, we saw a reaction occur in those cases with our nucleophiles. When we move to our carbonyls, what happens? Our leaving group isn't quite as good. We generate O-. That's not a very stable leaving group, and we can see the reverse reaction occur. Okay, so it's kind of an odd comparison, but it does work. So overall mechanisms when we go through and evaluate these. Okay, they go through and do a whole bunch of different versions of this. I think we will go ahead and stick with this as it is. So if we assume that our nucleophile is strong enough to attack, okay, so we'd be looking at carbon as a nucleophile, or maybe a hydride. Okay, so our nucleophile comes in, shares its electrons with the carbonyl carbon. That carbon now has how many bonds once it shares? 5 bonds. Can we have 5 bonds? No. So as with all mechanisms, we share our electrons, form a bond, then we have to evaluate, is that a stable species? If it's not stable at all, we have to fix our arrows. In this case, what's the arrow we need to fix? We have to break a bond. What bond do we break? Why do we break the pi bond of our carbonyl? It's our highest energy electrons, which makes it the easiest. So we break that pi electron, or that pi bond, and push those electrons onto the oxygen, and we'd get our first product. What we're assuming in this case is that this reaction favors our product. Okay? If it didn't favor the product, that proton transfer reaction at the end is pointless because we never form that intermediate. So we would have to assume that our nucleophile is strong enough to do the attack. Once it does the attack and we generate our intermediate, we now have a reactive oxygen. How do we know it's reactive? It's negatively charged. How do we stabilize a negatively charged atom? give it something positive. Most commonly, what we're looking at when we're looking at our carbonyl chemistry is a proton transfer. It'll pick up hydrogen from the solvent. Okay? Alcohols, acids may be floating around. Water's probably the most common one. Okay? We can then protonate it, and we end up with our alcohol on that atom. Now we've neutralized that charge, and we're now happy with our final product. Okay? Questions about that general mechanism? How could we speed it up? Okay, if we add a catalyst, what do we want our catalyst to do? It goes back to the same logic we used in the EAS reaction for speeding reactions. Make the nucleophile a stronger nucleophile. Okay, in the EAS reaction, what did we do to make our nucleophile stronger?
Activate it.
We had to activate it. So to activate our benzene ring, what did we do? We changed the structure. Okay, how do we get our nucleophile to be more nucleophilic? We use a different nucleophile. Okay, so you need to be able to rank nucleophile strengths. The common one that keeps popping up that I keep seeing people miss on. OH minus versus NH2 minus. Which is our stronger nucleophile? Why is NH2 minus the stronger nucleophile?
Because nitrogen is more willing to give up its electrons.
Yes. Why is it more willing to give up its electrons? Because nitrogen is less electronegative than the oxygen. It is more willing to give up those electrons. Nitrogen is a stronger nucleophile. Okay. What else could we do? So we can make the nucleophile more nucleophilic, or make our electrophile, our carbonyl carbon, more electrophilic. How can we make it more electrophilic? To become more electrophilic, what has to happen to it? It has to lose electrons. Everything in organic chemistry is about moving electrons. To make something more positive, what do we have to do? We have to take away negative charge. Take away electrons. Where's the easiest source of electrons around that carbon? The pi bond. Why the pi bond? Higher in energy than our sigma bonds. Okay? So we want to get those electrons pushed onto the oxygen better. How can we make oxygen really want to take the electrons away from the carbon? We want to react it with something that does what to the oxygen? Okay, if the oxygen becomes negative, does it need to take electrons from our carbon if it's negative? No. What charge do we want our oxygen to build? A positive charge. How can we get our oxygen positive? Let's take those electrons, one of those lone pairs, and instead of it being a lone pair, let's turn it into a bond to something that's easy to put on and off, a hydrogen. We could add an acid. That makes our oxygen formally positive. Does oxygen want to be positive? No. What does it do? It takes the pi electrons, and we now make our carbon positive. The carbon is more likely to be positive over our oxygen. We now have a formal positive charge on the carbonyl. There's our better electrophile. Okay? So it's all a question of pushing that electron density around, shifting it to see what you can force to happen in different circumstances. Okay? So here we go. How does adding that acid help? If we protonate our oxygen, it becomes positively charged because it's now sharing electrons with an extra atom. Why does that make our carbon more positive? What's our resonance structure? Yeah, go ahead.
Oxygen takes the 5 electrons away from the carbon.
The oxygen will withdraw the electrons from our carbon. Why?
Oxygen's more electronegative and wants to separate.
Oxygen is more electronegative than our carbon. So it picks up its lone pair as I draw that over the text. I'm sure everybody loves it when I do that. And what happens to our carbon? Formally positive. we now have a structure generating more positive charge on that carbon. The more positive our carbon becomes, the more electrophilic it is. The more electrophilic it is, what's going to happen to the reactivity of our carbonyl? It's going to become even more reactive. Okay? So what we're trying to do is push our reaction, okay, by evaluating that pi bond chemistry and really trying to drive the electrophile to become more electrophilic, okay, or see how our different substituents adjust it. Okay? So if we think back to the ketone aldehyde ester argument that we had, which would react slower, the ketone or the aldehyde? The ketone. We've got two explanations for it. Why should the ketone react slower? Steric hindrance. Okay. What else? We're looking at carbon versus hydrogen. What's the difference between carbon versus a hydrogen? What size have to do with it? So it comes back to size. How do we get bigger? How does any atom get bigger? It has more electrons. So our primary difference between hydrogen and carbon, carbon has more electrons, which does a steric effect, but what do those more electrons have the potential to do? Inductively stabilize the positive charge on our carbonyl. Okay? Our carbons are actually giving a little bit of electron density up to that carbonyl to help stabilize it. The hydrogen doesn't have that ability, so we get a steric effect and an inductive effect. If we push to resonance, what functional group gives us resonance stabilization of our electrophile? It's a hint, it's not the aldehyde or the ketone. The ester. What happened with our ester? Instead of it being carbon or hydrogen, we had an oxygen. What does that oxygen have on it? Lone pairs that can resonance stabilize that carbonyl carbon, making it even less reactive. So what we're trying to do is evaluate the electrophilicity of that carbon and rank all of the possible things that are contributing to it. Do you have to rank all of these for every single problem? If I give you an aldehyde, do you care about the ketone or ester reactivity? No, why not? Because you have the aldehyde. So this information is there to help you build on it. You then have to apply it. So you have to be thinking about the reactivity of that electrophile each and every time. So every new problem that shows up, we don't care about most of the peripheral. All we care about is aldehyde, ester, and ketone, at least at this stage. Okay. Are there other functional groups that have carbonyls? Carboxylic acid was the easy one. Give me another one. Let's push your abilities. Arguably the most important functional group for biochemistry. Not an ether. The amide functional group. So we're looking at a carbonyl with an NH something next to it. Why is the amide the most important for biochemistry? DNA, proteins, all your amino acids, how do they link? Through amide bonds. Okay? So having a good understanding of what makes your nucleophile so that it can react with the electrophilic carbonyl is really going to push and allow you to apply that information to biochemistry. Or, as most people will end up doing when it comes to biochemistry, what do you do instead? My favorite thing to do, memorize. So instead of understanding anything about the chemistry that's occurring in biochemistry, you ignore the chemistry part of that name, you look at the bio end, and you just go, oh, I just memorize it. Okay, that works. You can do it that way too. Okay? The idea behind this section of the material is to build that fundamentals so that you can then apply it to biochemistry and start to be able to predict how things will break apart and come together. Okay? Dang, we didn't even get to hydrogens yet. So we just looked at our acid reaction. We can protonate. Okay? We've been discussing this, though we didn't see the actual mechanistic steps. We'd react our carbonyl first with our acid. The acid supplies what atom? Give me a little bit more than hydrogens. Proton, so H plus. What do we need to react with a positive charge? Negative. Where do we have negative? Our oxygen. So we can take the electrons from our oxygen to react. Why did they take the lone pair and not the pi bond? Which is higher in energy? At least how we've been talking about it. Pi bond, because we're looking at p orbitals for our electrons, whereas our lone pair are located in what kind of orbitals? sp2 in this case. So we're looking at hybrid orbitals. Why use the lone pair? Does it matter? What's a resonance structure for this guy? Okay. We could take the pi bond out, and we'd end up with this as our result of using the pi electrons. Or we could use the lone pair, and we end up with this result for our arrow pushing. What's the difference between those two? Pseudo trick question. Absolutely nothing. Okay, it's not even when the nucleophile attacks. There is absolutely no difference between those structures. They both equally represent the exact same compound. Okay, that is the definition of resonance. So way back when you first learned about resonance, they said provide the structures for carbonate, CO3 minus 2. If you drew only one structure, your teacher should have taken off 2/3 of the points, minimum. Why? Because carbonate has 3 resonance structures. You absolutely must specify all 3 resonance structures, okay? Because they're all of equal energy. Same thing is kind of going along these lines, okay? Once we've got our now activated carbonyl, we can react with our nucleophile, and we end with our final result, okay? So we can run under neutral to basic conditions, which we saw first, or we can acidify it to activate the carbonyl and allow that reaction to happen a little bit smoother. Okay, they bring it here, they don't talk about it quite here. Okay, questions about that? Okay. Oh, here's the question that I was expecting them to ask. Why is an acid not used with a strong nucleophile? Okay, so the way they've got this drawn, it sure looks like the nucleophile is attacking as a strong nucleophile. How do we know it's attacking as a strong nucleophile? No, well, that's not a bad analysis there, but I want to go even further back. Let's ignore the product. How do we know this symbol, that nucleophile, is a strong nucleophile?
Formal negative and
It is formally negatively charged. That negative charge is a big tip-off. We're looking at a strong nucleophile. Okay? Why is it a bad idea to show a strong nucleophile in the presence of an acid? What other species are negative? Nucleophiles and Bronsted-Lowry bases. If it's nucleophilic, in a lot of cases, it is also a base. What happens when you add the strong acid? Neutralizes the nucleophile. So cool, you can now activate your carbonyl, but now you don't have a nucleophile to react with it. Okay? So it's a delicate balance between what you're going to do with those individual conditions, and you have to be careful with what you choose. That was further away than I thought. Okay? Questions about that? Okay, then we'll keep moving. So hydrogen nucleophiles, into the review stuff. We're done at 55, right? Okay. All of this is review, so I don't really want to spend a lot of time talking about it here. We can kind of go through some of it. The question that it mentions at top, why do we rarely see hydrogen acting as a nucleophile? What makes it hydrogen nucleophile? we'd have to do H, lone pair, negative, right? Why is that not stable? It's negative, which is our first pass, but we knew that. The more primary reason why it's extremely reactive is it's extremely small. We've condensed a very relatively large amount of electron density into a point. That makes it extremely reactive. Okay? So it's very rare to see hydrogen acting as a nucleophile because it's very rare to see hydrogen with a negative charge. Okay? So we have to use some reagent that will help hydrogen stay stable for long enough that we can get it into a reagent form. There's really only one or two elements that we can mix our hydrogen with that will allow for that reaction. What are those two elements? You might be able to guess one because it shows it up there. What elements can we combine to stabilize hydrogen or hydride at that H minus? There's only two elements, which means good for you, there's only two reagents. Boron is a great element to stabilize the hydrogen or the hydride. Why does boron work to stabilize it? It has an empty p orbital. Draw the electron or the Lewis dot structure for BH3. Okay? It has an empty p orbital in its neutral state. What can we put into that empty p orbital? The electrons from our hydride. Okay, so there's boron being our really good reagent. That's our sodium borohydride. What's our other reagent? Don't tell me L, A, or H. Aluminum. Okay, for our lithium aluminum hydride. I don't know, that was weird. Okay, why does aluminum work to do it? It's below boron. Why does that make it special? What happens within a column? The chemistry is the same. We get the exact same electron configuration. Between these two, which one's more reactive? The lithium aluminum hydride. We did talk about brief reasons behind that. We won't go into it again. You can talk to me later about it if you want. Okay? So both of these reagents, what you need to remember is they provide you a hydrogen nucleophile. You get hydride. What's a nice easy way to remember that? What is NaBH4 called? Boro what? What is sodium borohydride going to supply? Hydride. There's our nucleophile. What is LAH? Don't tell me LAH again. Lithium aluminum hydride. What is that reagent going to supply? Hydride. There's again our hydrogen nucleophile. Okay. So when we go through and look at our nucleophiles, I'm not sure I really want to evaluate this too much. You do see that negative charge on the aluminum, and that's its formal charge. Just because it's formally negative does not mean that's where the reactivity is. Okay? With both the lithium aluminum hydride and the sodium borohydride, what ends up happening is you get your H, and I'm going to draw this as just our metal for lithium or aluminum or boron. The H minus starts to coordinate with our carbonyl. The metal can coordinate with the oxygen. Once they get close enough, we can get the electron shifts around, and we now generate or have added our hydride to our carbonyl. Okay? In both cases, actually, we have to cleave that oxygen-metal bond. How do we do that? In the case of lithium aluminum hydride, what do we use? It's the next step. You add acid. We add the HCl. That dilute acid will cleave that bond and will be okay. How do we do it in the borohydride? As a hint, that bond is a lot weaker. If the bond is weaker, what can we get away with using that's going to be easier to work with? A weaker acid. The weaker acid used in our sodium borohydride, some alcohol or water. Okay, when we did it in the lab, they really pushed saying that the water was the one doing it. Your alcohol will also do it, just not to as large of an extent. Okay. Blah, 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 blah. I guess the last question, why do we do it in 2 steps with the lithium aluminum hydride? Why do we not just mix our carbonyl, lithium aluminum hydride, and acid all in one pot?
The acid would go into the oxygen in the first step.
It will do that, but that's not going to be important, actually. It's not going to be why we do that. The lithium aluminum hydride is extremely reactive as an H-. Okay? So it will react as a nucleophile as long as we give it the time to react with an electrophile. But because it still has that ability to act as a nucleophile, it can react and will react with acids. HCl will pull that hydrogen off, and we'll get hydrogen gas instead of the nucleophilic attack. Okay? Acid-base chemistry typically happens first, then followed by your electrophile nucleophile. Okay? Which is the same issue we have with the sodium borohydride. How do we get around that issue in lab? No, we can't do that because one of the solvents could be water. We added a lot of the sodium borohydride. So we can get around some of those issues by adding a big excess of it. The other reason why we aren't as concerned about it with the sodium borohydride is it's not as reactive, okay? Which means it'll take a little bit longer to react, which means we can potentially get it to react with the carbonyl because we've drawn out that time frame, okay? So those hopefully are, mechanism stuff. So there's the mechanism showing all of that. We already talked about those individual steps. Notice in the mechanism, they don't specify it's step 1 followed by then step 2 happening in the next case. Okay? Realize your mechanism will probably run everything together. Every single step, all the individual workups, anything else like that. But it is still officially has to be 2 steps. Okay? We'll at least talk about it. Okay? Carbon nucleophiles. We've got a variety of reagents to generate carbon nucleophiles, or really just 3. We've talked about all 3 so far this semester. How do we get a negative carbon? Grignard reagent works really well. Okay? How do we get the Grignard reagent? Close. React a alkyl bromine, so we need that carbon in there, and the magnesium will intercalate or separate, put itself in between the bromine and our carbon. That's going to dump a lot of electron density onto our carbon. We now generate, they did such a great job of showing it in this picture, a negatively charged carbon effectively. Okay, so our Grignard reagent does a good job at generating a carbon nucleophile. How else can we get one? What was that? We've got the cyano as a possibility. That gave us a carbon nucleophile. Fun thing with cyano, you never mix that with acid. Why? It's pretty reactive. That's not the biggest issue. You get hydrogen cyanide, which is very, very toxic gas. Yeah, not particularly pleasant. Okay. If you ever have to work with those, anybody know the characteristic smell for hydrogen cyanide? Almonds. You smell almonds and you're working with cyano compounds, it's usually a good time to leave. If you've survived at that point. But yeah, when you're working with cyanide compounds, you typically want to not be present when you smell almonds. You get a little bit of warning, but not much. There's one more place that we can get a negative carbon. The cyano was kind of a big hint, or as big of a hint as I can give you on that.
Terminal alkyne.
If we had an alkyne that was terminal, what was special about the chemistry of that terminal alkyne, that carbon? It's slightly acidic. So we can react it with a strong base to pull off the hydrogen, and we now have, where's my color? Our carbon nucleophile. Okay? So we really have 3, and I think it's only 3 carbon or sources of carbon nucleophiles. Okay? Whereas all the other reagents, we have a couple different options. We will only see them as being A negative charge, why not larger than -1? If they were really reactive as -1, what do you think is going to happen when they become -2? It will probably destroy stuff. Okay, so we aren't going to get them up to that -2 charge. Okay, so I'm out of time. So